All right, kiddos, today we are going to talk about isomerism and structural formulas. If you remember some of your prefixes, the word iso means the same, and so we're going to be talking about some things that seem like they're the same but aren't quite the same. Okay, think back to the word isotope that we used in chemistry 1, where it was the same element, but it had different masses. We're going to have the same sort of deal here. So, we know how to do our molecular formulas. Okay, these are all really common compounds. We've got water, methane, ethanol, and what a molecular formula, of course, tells us is what types of atoms we have: hydrogen, oxygen, and then how many of each atom. Okay, pretty simple. So down here in an ethanol, I've got 2 carbons, 6 total hydrogens, and 1 oxygen. And we'll get back to why it's this way here in a second. A structural formula actually gives us some clues to what the molecule actually looks like. And this is going to be super important to us here in organic and biochem, because what matters a lot in the way that atoms interact isn't just what, or molecules interact, isn't just what they are, but what their shape is. Okay, and so they react in different ways. A lot of new medicines are sort of taking old compounds that we're already known about and just changing either an atom or maybe changing where that atom is on the molecule. And so the structural formulas really matter a lot. And so we've got a few different structural formulas here. Okay, so water, we can see that it's a bent molecule. Methane is a tetrahedral molecule. Of course, these are 2D images. And then we've got ethanol here. And there are a couple of things that you should note immediately. You'll notice on the oxygens that we didn't draw all of the extra electrons. That's not really necessary for us in organic. In fact, we're going to strip it down even further than this a little bit later. And you'll also note that here on this OH here, which is what we call, that's a hydroxyl group, an alcohol group, basically, we would say. This oxygen could have been over here, it could have been over here. As long as it was an oxygen with this H attached to it, it really could have been in any of these positions also, and it would have been the exact same molecule. Okay? Now, back to this idea of why would we write it like this? I know back when we were doing percent composition and things like that in Chem 1 that this tends to drive students bonkers. Why didn't you just put all of the H's together? Okay, that would make life a lot easier. Well, the reasoning behind that is because this gives me some clues into what the actual shape of the molecule is. Okay, but what if we didn't do that? What if we just wrote it as C2H6O, okay, which I think we would agree is the same formula, basically, just written a little bit differently. Okay, so let's work off of this one now, and we'll get rid of that one. So same molecule here. The difference is I don't really have a clue that there's an OH group in this. In fact, it doesn't have to be an alcohol at all. Okay, so we know this is an alcohol, this is ethanol. But we can actually draw this same chemical formula here. We could draw the structural formula look entirely different. Okay, we put this oxygen in the middle. We got 2 methyl groups hanging off the opposite side. Organically, this is a much different molecule. This OH here is, again, hydroxyl group. It makes something an alcohol. This O in the middle here makes something an ether. And in fact, this molecule here is what we call dimethyl ether or methoxymethane. Okay, methoxymethane. We'll get to all those naming stuff in a little while. And these are vastly different molecules. These molecules really aren't anything alike at all. This one has a boiling point well below freezing, and what that means, of course, is this is going to be a gas at room temperature. Ethanol, of course, is not a gas at room temperature. It's a liquid, but it has a lower boiling point than water, so we could actually boil it off way before we got to the water stage. Of course, that's how they distill spirits. So these are vastly different molecules, but look, they have the exact same formula. Okay? We have a name for these kinds of things. Molecules that have the same kinds of numbers of atoms. In other words, they have the same chemical formula, okay, or molecular formula, we might say. But different arrangements of their atoms are called isomers. We are going to spend so much of our year talking about isomers of different kinds. There's more than one way we can have an isomer. There's more than one way we can have a molecule with the same molecular formula that its structure is different. There's just a vast number of different ways. We're going to spend a lot of time talking about that. These particular things, these are what we call examples of structural isomerism. That means that their structural formulas, the way that the atoms are actually arranged, are different. We're going to see later in the year, we'll see some other kinds of isomerism. But for right now, we're going to focus on structural isomerism, which means that they've got the same formula, but their structures are different, and that's going to make them vastly different molecules. Okay? All right, so let's see some other examples of this. So if we take another molecule, and you'll have to forgive as normal my writing, because remember I'm writing on the tablet here, so that makes it a little bit more difficult. So I'm going to draw a structure for this. Anytime, if you remember our lessons on this stuff from last year, we said if you've got a carbon, carbons usually go in the middle, and if you've got a bunch of them, like I do here, I've got 5, the easiest thing to do is just sort of chain them out. Okay, I'm going to draw them all in a chain, and then we would go in and sort of fill in around the chain with our hydrogens. Now, it's real important as you do this that when you're done, that you do go back and check valence. Now, you get to a point in the year where you're going to be doing these things so regularly and so used to it that you might not need to check valence as much because you'll be just drawing them right because you've done them 100 times. But just in case, it's always safe to go ahead and draw everything out. So this would be a pentane molecule. And again, we'll talk more about how we name these things later. That's a big part of the course, actually. But pentane here is basically this straight chain of 5 carbons, completely, we would say, saturated with hydrogens. We'll talk more about saturated and unsaturated again later on. But saturated basically just means that every empty spot is occupied by a hydrogen, which it is. And so that's sort of what we call normal or N-pentane. That's the normal way that we could draw it. But we don't have to draw it that way. We could actually draw it in a slightly different way. So if I took my carbons here, and instead of putting them all in a straight chain, let's say that I just branched one of them. Okay, so this would be a continuous chain. This is a branching chain because I've got something hanging off of it. Okay, and then of course we go back and I draw. Sorry, that hydrogen there looks like an A. Again, I apologize. Oh my gosh, we're going to blame all of this on the tablet, but these are all H's, guys. No, there's no A's. Okay, even though I'm going to continue to draw them. So we've got a bunch of H's here, and actually it looks like I think I missed a couple. Yep. Okay, same exact molecule. Okay, as far as its formula, C5H12. If you count these, there are 12 hydrogens. If you count all the A's as hydrogens, which they are. But this is a completely different molecule. This molecule is what we call isopentane, and technically it's not really. That wouldn't really be the accurate name anyway. What we'd really call this is methylbutane. So this is a completely separate molecule. This is a completely separate isomer. And in fact, there's one more isomer of this. So what I would ask you to do real quick is just pause the video, see if you can draw the other isomer of C5H12. See if you can find a different way to draw it that doesn't look like either one of these two, that is completely different, that shows a completely different structure. Okay, so hit pause and try that. All right, so hopefully you took a second to see if you could draw the other structure of C5H12, the other isomer, and it should essentially look like this. Again, hydrogens around all of the outside places. Okay. What you'll notice here is that I've got my carbons, my longest chain in this case. Whoops, I forgot to draw the bond lines. Those are kind of important. My longest chain here is only 3. Again, these are all H's, even though I'm having some issues. So I've got right through here, I've got 3 carbons here, I've got 3 carbons this way, completely different molecule. This is sometimes called neopentane. Really, this should be 2,2-dimethylpropane is what this would be. But this is a completely different molecule. Each of these molecules, each of these structural isomers is a different chemical. They don't react the same way. They've got different boiling points often. They react in different ways. So these are not the same molecules at all. So these structural isomers matter. We could have the same formula, but still have vastly different molecules. Now, for those of you all that actually did what I asked and you paused the video, what you may have noticed is you're like, well, wait a minute, I drew some of these. And so I drew one where I had the 4 carbons in a row, but then I put a carbon over here. That's really the same thing as what we drew before, because basically what it means is the branch is 1 carbon away from the end. Okay, so it's exactly the same thing as before. That would also apply if you said, hey, what if I drew it like this instead and I put it on top? Okay, still the same molecule. One thing that's kind of cool is that we can actually rotate around these bonds, and so basically I've just taken that molecule and sort of just turned it on this carbon here to put that carbon up top. So it's really still the exact same thing. Nothing has changed. Some of you might have said, well, what if I put it on a different carbon then? What if I put the branch on the end? Well, I mean, that's all well and good, but that's actually not a branch. That's still a row of 5 carbons, and that would also apply, obviously, if we stuck it off the end. So when we're doing any of our structures, what matters to us is the longest continuous chain. Even if it appears to branch, branches only go off of the longest chain. Okay? And obviously, we're going to practice a whole lot of this stuff in class. So, those structural formulas, they can get pretty weighty. I mean, there's a lot of stuff there when you've got to draw these out, and they will take a while. We're going to do tons of them. And it's going to take a while to be able to do all of those formulas. So this goes back to the 2 formulas that we've just done. This is pentane. This is the isopentane. Okay, so if you look back, this one and this one. Okay, yeah, they look a lot nicer here because I didn't draw them. We can actually abbreviate these structural formulas, and we can write them out almost in molecular formula way, but still keep all of the structure here. So what I could actually do is I could write this one as this. Okay, so C3, okay, hang on, let me grab a pen here real quick. So C3, okay, H2, H2, or CH2, 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 and then CH3. And that would give me this abbreviated structural formula. In other words, I could write it out without actually having to go in and draw all of the bond lines. And this would be an equally valid way to write that unless you were asked to draw it all out as a regular structural formula. If you're asked for an abbreviated one, you could do something like this. We do the same thing down here. Okay, CH3. Again, let me grab my pen. CH3 here. And then this is the CH that goes right here. Okay. And then the CH3 that branches is down here, and then CH2, CH3. And so you can sort of see we've got basically the same thing. And what I love about these sort of abbreviated formulas like this is this basically tells me what the shape of the molecule is. I can tell that no problem from looking at this the same way as I could looking at this. But it obviously takes up a lot less space, probably take a lot less time to put together. And in fact, we can actually abbreviate these even a little bit more. We could actually say, well, you know what, in the middle here, this is just repeating. Okay, I've got CH2 times 3, and so I'm just going to abbreviate that. That's CH2 times 3. Okay, if I did the same thing down here, I've got 2 CH3s hanging off of this same CH. Okay, so that's going to be a more abbreviated form, and then the CH2 and the CH3 there at the end. But, and let me completely blow your minds here for just a second. Let me erase some of this stuff real quick. What chemists actually do, organic chemists in particular, is we're really lazy. We really want to draw these things in the shortest possible way that we can draw them. And so what we do is we actually draw formulas like, structural formulas like this. And you're probably looking at that saying, well, how does that tell me anything? Well, this works because we're assuming that every carbon is completely surrounded by hydrogens, okay, which it is. And the way these particular forms here work, the way these line models work, is that at each point, at the end of each line, we're going to say that there's a carbon. So there's 1 carbon, 2, 3, 4, and 5 carbons. So I've still got all 5 of my carbons, okay? And if we came down here to the bottom, we would see the same thing here. So 1, 2, 3, 4, 5. So at the end of each line, there's still a carbon. And the rule is that unless there's some other bonds there or other molecules or other atoms drawn off of it, that each of these points is essentially saturated, that there are carbons completely surrounding it. Now, this stuff will take a little bit of time to get used to drawing them this way, but I got to tell you, once you get used to them, by the end of the year, this is by far the easiest way to draw these rather than drawing out these entire structures. Okay, so that's just a quick glimpse into structural formulas and isomerism. Again, that's going to be a big topic for us. We're going to talk about it a lot this year. And of course, as with everything we're going to do in organic, it's just going to take some practice. We're going to have to work on a bunch of these things. And of course, that's what we'll be doing in our groups. All right, thanks a lot, guys.